All right, welcome to page 4 of our notes. Here we have, again, the spring mass systems, but here we have free damped motion. So harmonic motion is unrealistic because it assumes that there is no retarding forces acting on the moving mass. In reality, there is at least a resisting force due to surrounding medium. The mass could be suspended in a viscous medium or connected to a dashpot damping device. Damping forces are considered to be proportional to a power of the instantaneous velocity. Well, we will assume that this force is a constant multiple of dx over t, or the first derivative. So from Newton's second law, again, what we have is our force on our right is equal to mass times acceleration, where now we're going to be adding to our force basically our retarding forces, our resisting forces, which is given by our constant multiple. The constant multiple is going to be beta times our first derivative. So that means the equation of free damped motion is just going to be our second derivative plus our beta divided by our mass. Again, we're just getting rid of that leading coefficient, plus our k divided by the mass, or another constant divided by mass, times x equals 0. Or, and what you'll most commonly see is this, the second derivative plus 2 lambda, where lambda, or 2 lambda, is our beta over our mass, which is a constant divided by our mass, and our omega squared is, once again, our constant k divided by our mass. And again, the reason why they're written this way is so that when we are working with taking our, solving our differential equations, it's a little bit easier using the 2 lambda and the omega squared. And so now the auxiliary equation is going to be m squared plus 2 lambda m plus omega squared equals 0. Because we have this, what we can do is, in order to solve for our m's, our m sub 1 and our m sub 2, we could use the quadratic equation. If we use the quadratic equation, our b would be 2 lambda, our c would be omega squared, and our a would just be 1. This is what we would have after we're using our quadratic formula. That m sub 1 is negative lambda plus the square root of lambda squared minus omega squared, and our m sub 2, which is negative lambda minus the square root of lambda squared minus omega squared. So for case 1, lambda squared minus omega squared greater than 0 means that the system is overdamped, that there is a lot of forces acting against, or not a lot of forces, but the force is pretty big that's acting against our spring. And if this is the case, it's just kind of like case 1, where we're going to have two solutions. It's going to be c sub 1 times e to m sub 1 of t plus c sub 2 times e to the m sub 2 of t, which can be more simplified to this. X of t is equal to e to the negative lambda t. I'm going to rewrite this just so that's easier to see on the notes. So it's going to be x of t is equal to e to the negative lambda t. We're just going to pull that out because that negative lambda is happening in both cases. Times c sub 1 e to the square root of lambda squared minus omega squared t plus c sub 2 e to the negative square root of lambda squared minus omega squared t. And that would be our solution when lambda squared minus omega squared is greater than 0. So that's what we want. We want to check to see, okay, is our lambda squared greater than our omega squared? Because if it is, then it's going to be positive. And so this would be our solution. Now, if we go to case 2 and we have lambda squared minus omega squared, if that equals 0, then we can say that the system is critically damped. So meaning that our resisting force that's applied to it, is going to be so great that instead of having, our spring go up and down until it gets until it gets back to the equilibrium position, it could just be where it only passes through the equilibrium position once before it gets back to it, instead of going a few times. So it's pretty strong considering that we have a spring. So if this is the case, our m sub 1 is equal to our m sub 2. And so we know what happens if that's the case. We're going to have our position function is going to be c sub 1 times e to the negative lambda t plus c sub 2 t e to the negative lambda t. So because our solution repeated twice. Because this is the case, we can simplify it as x sub t is equal to e to the negative lambda t times c sub 1 plus c sub 2t.